Greetings everyone. So till now we have studied about the conduction heat transfer when there is variation of thermal conductivity with temperature. We saw that if there is variation of thermal conductivity in linear fashion like that, then for plane wall we saw that temperature distributions come out to be T minus T1 divided by T2 minus T1 equal to x time x by L times 1 plus minus beta times T1 plus T2 by 2 divided by 1 plus minus beta T1 plus T by 2, and also heat transfer for this particular case is T1 minus T2 divided by L and then whole divided by K naught 1 plus minus beta times T1 plus T2 by 2 times area. Area is the cross-sectional area of the plane wall. Okay, and this thing we have proved from the last class that this is nothing but the K average value of thermal conductivity in the range of T1 to T2 temperature. Right, so we can write like T1 minus T2 divided by L divided by K average times area. Okay, so far this we have seen. So for second case, when there is variation of thermal conductivity with temperature, but in case of hollow cylinder, right? So T minus T1 divided by T2 minus T1 by equal to ln R by R1 divided by ln R2 by R1. Right, we have seen this derivation when there is steady state temperature distribution, no internal heat generation, and thermoconductivity is constant. So this thing we have seen before. Okay, so just keep this in mind. I will show you some results when we derive the result for this particular case. So hollow cylinder, let's suppose this is a hollow cylinder, this is the center of the cylinder, this is R1 radius, R2 radius, and thermoconductivity again varying with temperature. Right, so we have to find the temperature distribution as well as the heat transfer through this hollow cylinder. Let's suppose the inner wall and the outer wall are maintained at different temperature T1 and T2, and assuming T1 is greater than T2. Right, so again start with Fourier law in the radial direction. K times A, area is nothing but 2 pi R times L times temperature gradient in the radial direction, which is nothing but dt by dr. Right, and this r is any particular radius from the center. So writing K as K naught 1 plus minus beta times T 2 pi r L times dt by dr. So let's do integration for that. Q is constant. Okay, for this case because it is steady state. So whatever heat coming out of this plane, the same heat will be going out of this plane, right? So we can have dr by r this side, and on the right hand side, except 1 plus minus beta t, everything is constant. So keep this out of the integration, pi times L, and inside the integration will be 1 plus minus beta t dt, right? So integrating from r1 to r, and at r1 temperature is T1, at r temperature is T2, unknown temperature, okay, and r is the any radius. So if we integrate, we can have q times ln r by r1 on the right hand side, q naught plus minus, let's suppose we are integrating it for okay, leave it, 2 pi l times 1 plus, this is t, beta t square by 2 minus t1 plus minus beta t1 square by 2 whole divided by plus minus beta. Right, again integrating from r1 to r2, integrating r1 to r2, so we can have q equal to minus k naught 2 pi l t plus minus beta, this is t2 beta square minus t1 plus minus beta t1 square by 2, right, divided by ln r2 by r1, right? So dividing 1 and 2, we can have the temperature distribution. Also here we have plus minus beta, dividing 1 and 2, so we can have temperature distribution if we rearrange. So you can take it as an exercise. So we can have t minus t1 divided by t2 minus t1 times equal to ln r by r1 divided by ln r2 by r1 times 1 plus minus beta times t1 plus t2 by 2 divided by 1 plus minus t1 plus t by 2. So right, this is the temperature distribution, and for heat transfer we can write like, after arranging, we can write from this the heat transfer will be T minus T2 divided by ln R2 by R1 divided by 2 pi k naught 1 plus minus beta T L, which is nothing but T1 minus T2 divided by ln R2 by R1 divided by 2 pi k average times L. Okay, so after rearranging and all, we can find find this. If you find any difficulty, you can ask me. I will clarify it, that how this thing has been derived. Okay. So similarly, we can find for hollow sphere. I am giving you the result. You can try by yourself and see. If you have any doubts, you can just ask me in comments. So this is the temperature distribution for hollow sphere by R1, 1 by R2 minus 1 by R1. This whole thing multiplied by 1 plus minus beta T1 plus T2 by 2 divided by 1 plus minus beta T1 plus T by 2, right? And heat transfer is T1 minus T2 divided by 1 by 4 pi K average, mind it, 1 by R1 minus 1 by R2. Okay, so this is all about the heat conduction when there is variation of thermal conductivity. So sorry, one thing I forgot to tell you, that for steady state heat transfer, when there is no variation of thermal conductivity and no internal heat generation, we got this temperature distribution. But when there is variation of thermal conductivity and all other things are same, we got the temperature distribution like this. See, you can see only this thing is the previous one, and this factor is coming extra when we have variation of thermal conductivity. Okay, so there is beta also here. Okay, so if beta is 0, means no variation of thermal conductivity with temperature, and this term will vanish and will go to 1, and we are left with only this terms. Okay, and this is nothing but and this will boil down to the previous case, which is nothing but steady state internal heat generation and Ks constant. Thank you.